Good evening, everyone. My name is Riaz, and my topic is related to the hydrogen liquefaction. And this work is partly worked out co-authored with Natash and my professor, Professor Mungungi. We have talked about the different aspects of climate change and other things, but let's discuss what we are going to present today. These are some of the introduction, followed by the basics of the hydrogen liquefaction that we will cover just to make sure that everybody's on ground. And then I will go with the challenges associated with hydrogen liquefaction, some of the motivation for this particular work, the simulation basis, associate some results, and final conclusion. Now, before we go into the detail about the introduction or anything, the world that we are living in today, we have all talked about the climate change and everything, but what is actually happening around us? We cannot take our eyes away from it. So there are flash floodings, and at the same time, rough drafts, typhoons, melting ice. All this is because of just the tip of the iceberg. What is going to come up in the next 10 to 20 years, we still cannot comprehend what is going to happen. So the world over, we have agreed that we will go for the CO2 abatement as a basic procedure. So we have the target to reduce the 50% of CO2 emissions. And for that particular reason, we need to minimize the use of fossil fuel, of course, but at the same time, we have to maximize the use of renewable energy. But with the renewable energy, there is a catch. With every solution, there is a catch. So with the renewable energy, we have the problem of intermittency and security of supply. These are the two core issues related to the renewable energy, but there is another one. There are areas in this world which are rich in renewable energy, but the utilization of energy is low. And then there are areas where utilization is high, but the production or the production opportunities for the renewable energy are very low. So in both cases, we have to transport energy, and in such a case, hydrogen is generally considered as the energy carrier. Now, we know hydrogen is the lightest and most abundant of the components in the universe, not only on the Earth, but in the universe itself. But it is not freely available. It has to be produced just like electricity. That is why currently we are relying on the fossil fuels, like most of the time, more than 80% of the time is produced from the reforming of natural gas. But if we are going for the green hydrogen, of course we can produce hydrogen. That is one way, but where it can be utilized? Australia or maybe Northern Africa, southern other countries, they have high potential of producing hydrogen from green hydrogen, but the utilization is not as much. Utilization maybe in Korea, they are importing. In other countries, America, they are importing. Japan is importing. So how they are going to transport or store hydrogen? These are the different methodologies. Just why we are interested in hydrogen only is because of this high gravimetric energy density. This is the highest among all the known fuels in the world. So, but since it is at the low end, because of its low volumetric energy density, which is very good in terms when we go for the storage and for transportation sector. So the volumetric side is important at times. At this point, it is very low on the y-axis. Only the liquid hydrogen gives us an opportunity because liquid hydrogen is higher density relatively, and because of the higher density, we have a higher volumetric value here. Now, with the hydrogen liquefaction, it's not a new thing that is going to happen. Since 1950s, since the start of the rocket or the space war, we are having the liquefaction cycles. So this is just the one latest process in the commercial sphere. And this flow sheet is from the Ingolstadt plant in Germany, operated by Linde. And this particular process, as you can see, we have, this is a pre-cooling cycle, generally stages. We have pre-cooling, then we have the cooling cycle, and the last is the liquefaction. 3 steps of producing the liquid hydrogen. So the first phase brought down to minus 195 degrees Celsius using liquid nitrogen. Then the second phase is using these 4 exchangers, cryogenic exchangers. So we bring it down to minus 243. And then from here, we go down to minus 251 0.8 degrees Celsius, which is the boiling point of hydrogen. Now, apart from all these, we use liquid nitrogen as a refrigerant in the first cycle, but then the later sector, we use either the expanders or the liquid hydrogen in itself as a refrigerant. And then there are, you can see these reactors here, 1, 2, 3, 4. These are the 4 reactors available within the hydrogen system. So the 2 reactors are isothermal phase and 2 are adiabatically operated. Talking about the reactors, I will go into detail in the next later. But for these particular plants, usually they have a range of specific energy consumption, SEC, which is related, generally lies in the 12 to 15 kilowatt hours per kg of liquid hydrogen. For this particular plant, it's around 13.58 kilowatt hour, which is a very high energy consumption. So our major objective is to reduce this energy consumption if we are going to make liquid hydrogen as an energy carrier in the market. Talking about the reaction, hydrogen in itself actually exists in 2 different quantum states. Orthohydrogen, which have the same nuclei spin, and the parohydrogen, which have a different nuclei spin. So in the normal state, hydrogen exists 75% of ortho and 25% of para. This is the normal state at equilibrium in the atmospheric conditions, ambient conditions. Now, with the passage of time, this is the equilibrium curve. As the temperature goes down, the equilibrium shifts towards the parahydrogen. So the parahydrogen concentration increases gradually as the temperature goes down. So, but this reaction, as you can see, is a very slow reaction in the high temperature zone. As the temperature goes beyond 100, the rate actually increases. But this overall reaction rate is very slow, so we have to catalyze the reaction. And why we do need to do it? Some people initially used to say that we do not need to convert it to parahydrogen, but this graph gives you a good idea, because if you want to store hydrogen and transport hydrogen over the longer distance, like intercontinental states as well, so we would like to have as much as liquid fraction as possible. But if follow this one, 75%, which means there is no conversion, so all is orthohydrogen. So if we do not do it, as the time goes on, this particular Y fraction represents the liquid fraction. So the mass of the liquid fraction actually decreases from around about 99% to roughly about 32-33%. So all the effort that we put in, all the energy that we put in to liquefy hydrogen actually goes down the drain. We do not want that one. So we try to convert this ortho to para so that we can reach here to have maximum value of liquid hydrogen. We have a publication on this one as well, detailed about this particular part. But right now, talking about the process of hydrogen liquefaction, why we are actually doing it. We actually, initially when we started with the hydrogen liquefaction process, we started with a 2-stage process rather than stages in this case are considered based on the number of reactors. In the commercial process, as I showed, it actually has 4 stages, 4 reaction stages, but in our particular first process, we decided to have 2 reactors. When we designed this particular process, and we actually have published this one as well in ECM, but we saw that in the pre-cooling stage, in the very first stage, we have this huge gap here between the composite curve. This composite curve is of the first heat exchanger. So it shows that the big gap here, with the gap between the hot and cold composite curves, it shows as the inefficiency of the process. So we tried to reduce this one, and then the same curve, if we plot it on the approach temperature, the difference between the hot and cold composite curves, the maximum is around 33. So there is a huge potential of reducing this gap, and we can save more energy here. For that particular part, we tried to do another simulation with introduction of, since it is at the hot end, so we need a high boiling point temperature. That is why we chose hydrofluoroolefin. It has already been studied and used for LNG cases as well. So we tried it here. And before I go for the detail, let me show you the simulation assumptions that we take usually. Most of the time, when we saw the literature, there have been a big boom in the hydrogen liquefaction studies in the recent times. And most of the studies are using S1-HYSYS, so we use the same software. And following the trend, the same as the research for PENGRO. PR actually here stands for PENG Robinson, the fluid package that we use for estimating the physical properties of the components involved in the mixed refrigerant system. There are other as well. NM here actually stands for not mentioned. So there are a huge number of publications which do not actually mention the fluid package is being used, which is a very essential part when it comes to the design or the process simulation studies. So in our case, we have used standard conditions. These are the standard conditions for all the process conditions, because 21 bar is usually the pressure that we obtain at the end of SMR, the methane steam methane reforming. That is a usual case. 25 degrees Celsius ambient conditions, but these are the conditions every process design that you will see in the literature will use the same conditions. So as I mentioned, autopara concentration at the start point is the same. So we use the process conditions for every compressor efficiencies and expander efficiencies, and then pressure ratio will be considered less than 3, not more than anything. That is the maximum cap that is used by the industry. And meta values, minimum internal temperature approach is ranged between 1 to 2 degrees Celsius, which is a quite norm in the case of cryogenic liquids such as hydrogen. Even in case of LNG, it's around 2 to 3 or sometimes 3 to 5, but it varies. But for the hydrogen case, it's very normal that we keep it at 1 to 2 degrees Celsius. So from our previous, as I mentioned in the motivation section, that we utilized 2 stages, but we tried to change it. We saw that if we increase the number of stages, the energy efficiency also decreases. So we tried to increase 1 more reactor here, so increase the number of stages, and we introduced the hydrofluoroolefin in the pre-mixing cycle. Previously, we were using C1, C2, C3 nitrogen, and in the pre-cooling section. In the cooling cycle, we are using the same with hydrogen as well. But the last cycle, which used only here hydrogen and helium. So our cycle actually starts from hydrogen here, then we have the reactor, 3 reactors. So ortho is converted here, but only the equilibrium composition is considered. So as a temperature here, so that at that temperature, what is the normal composition? Using the equilibrium curve that I have already showed, so we utilize the data, and in using the data, we have simulated the reactor to have the para-hydrogen concentration. At the end, we have around 99.5% para-hydrogen, which is actually the demand of the industry, which is the requirement for the industry. So we utilize the same, the 3 refrigeration cycles have been used in this particular process. Based on the studies, we actually designed 4 cases. So first is the unoptimized 2-stage process, which was the earlier published case. So we utilized, that was considered the first. Then we optimized the unproposed case. Then we optimized it. And then introduced the HFO and optimization again. These are some of the results that we obtained. You can see that these are the refrigerant flow rates in the individual cycle, individual cases. Although the first case basically is the base case, BC stands for base case, PC for the proposed case. So we have the final proposed case is the PC2. This one, although you may see that the refrigerant quantity is here is low, but if we compare it as compared to the energy, then the energy would be higher consumption in this particular case. But these processes, if we compare with the first one, the refrigerant flow overall is almost same. But individual fractions, I couldn't present it here, but those details are available. But if we go for the detailed composition, that is slightly different. And when we saw the meta values, you see the unoptimized case is more than 3, but in the perfectly optimized value, we have around 1, slightly above 1, which is a very good result for meta values. Similarly, the para-hydrogen composition, I showed you 99.5%, and then the stage temperatures that we have for this particular process, they are almost the same in all processes. So slight variations only. In terms of the composite curves, if you see that this was the first case that we had, the one, and the final case we actually reduce the gap even on this side as well. And if you go for the approach temperature, we have to reduce this curve. Previously it was around here, and we reduce this gap down to this particular point, which means that we have reduced the energy consumption in this section only. In terms of exergy destruction, this gives us an idea of how much exergy is being discharged and in which section is going down. So we can see that exergy is actually reduced as in the optimized case, it's almost half. Similar is the case for the SEC. So initially it was 10.515, which was still less than the commercial process, but now for both cases around 5.9, which is very, very low value and very good value. And the overall energy savings are roughly around 42%. Actually, this study has already been published in hydrogen energy as well. And these are some of the statistics for the same representation of the energy and exergy efficiency, which is the highest 51% in case of our post case. Overall, if we conclude this process, we can see that the complexity of the process has played a major role. So our target was to reduce the complexity of the process. So we utilized a simple design, and simple design was able to give us more high efficiency and reduce the energy consumption. And also we were able to reduce the 50% energy saving in this particular case. These are some of the acknowledgements that I have to acknowledge the financial grants that we have received. And thank you very much for